So today, we are going to talk about a single elementary particle. And I know that might not sound like a big deal, but this one is different. It's a particle so fundamental and so unbelievably hard to find that it took over 40 years and one of the biggest machines ever built by humanity just to prove it exists. And in doing so, it confirmed everything we thought we knew about reality. This is the story of the Higgs boson.
But really, our story starts with a question, a huge one. Just look around you for a second. Everything you see, everything you are, has substance. It has what we call mass. But where does that actually come from? I mean, why do some particles have mass and others, like the particles of light streaming from your screen, have none at all? Answering that was one of the greatest scientific quests in history. And to really get why it was such a quest, we have to go back to the biggest puzzle in 20th century physics. You see, scientists had this incredible theory that was almost perfect, but it had one giant, gaping, universe-sized hole right in the middle of it. Okay, so let's talk about this theory. It's called the Standard Model, and you can think of it as the ultimate recipe book for the universe. Seriously, it describes all the fundamental particles. You know, quarks, electrons, the whole gang, and the forces that tell them what to do. And it does it with absolutely stunning precision. It was, and still is, one of the most successful theories we have ever come up with. Now, the idea at the very heart of the Standard Model, the thing that made it so beautiful and powerful, was this core principle: symmetry. The math just worked out perfectly. It relied on this deep underlying symmetry between the forces of nature. And this wasn't just about looking pretty. This symmetry was the engine that gave the model its incredible predictive power. But here's the massive problem. That beautiful, essential symmetry made a very clear, very specific prediction. The particles that carry the weak nuclear force, these things called the W and Z bosons, they had to be massless. They just had to be. But when we actually looked for them in experiments, it was the exact opposite. They were incredibly heavy, some of the heaviest particles we had ever seen. The theory said one thing, but reality was screaming something else entirely. Physics was completely stuck. The solution, first cooked up way back in the 1960s, was, well, it was radical. What if the universe wasn't empty? What if permeating every single cubic inch of space, there was some kind of invisible field? You know, as the physicist Philip Anderson once said, physics is pretty much just the study of symmetry. So this was a huge paradox, right? How could the laws of physics be symmetrical if some of the key particles clearly weren't? Well, this new idea proposed a brilliant way out. Maybe the fundamental laws are perfectly symmetrical, even if the universe we happen to live in doesn't always look that way. It's a concept called spontaneous symmetry breaking. Here's a way to think about it. Imagine the early, super hot, high-energy universe is like a ball balanced perfectly on the very peak of a hill. Any direction it rolls is possible. The situation is totally symmetrical. But as the universe cooled down, that ball inevitably rolled down into the valley below, picking one specific random direction. Now, the hill itself is still symmetrical, but the ball's final position has broken that perfect symmetry. And that is the Higgs field, a field that, unlike any other we know of, has a value greater than zero, even in totally empty space. It's the valley that our universe settled into. And as other particles move through this field, they interact with it. They kind of drag against it. And that interaction is what we perceive as mass. But this theory made one absolutely crucial prediction. If this field is real, there has to be a particle associated with it. And with that incredible prediction, the race was on. A 40-year, globe-spanning, multi-generational hunt for the physical proof of the Higgs field, its particle, the Higgs boson. And let me tell you, the stakes could not have been higher. Finding this particle wasn't just about discovering something new. It was about validating the entire Standard Model. If the Higgs didn't exist, our whole picture of fundamental physics was basically wrong. It really was the central problem for decades. The sheer scale of this effort was just immense. I mean, the theory gets proposed in 1964, and then decades go by, nothing. Big experiments at CERN in the 90s found absolutely no evidence. It wasn't until the unbelievable power of the Large Hadron Collider came online that we finally started to see the first tantalizing hints. 300 trillion. That's roughly how many proton-proton collisions scientists had to create and then sift through to find this thing.
It's like trying to find one specific grain of sand on every single beach on Earth. The scale of that task is just monumental. So all of that effort, all of that data, it all came down to a single historic moment. But you know what? Finding a little bump in the data was just the beginning. Then came the really hard work of proving what exactly it was. So picture this. It's July 4th, 2012. The world's entire scientific community is holding its breath. In a packed auditorium at CERN, with physicists all over the world watching online, the leaders of the two giant LHC experiments got up and announced the results. They had both, independently, discovered a new particle with a mass around 125 giga-electron volts. For a single elementary particle, that is heavy. This was a huge deal. The announcement was just electrifying. With these very carefully chosen words, the head of CERN basically confirmed it. Both experiments, working totally separately, had seen a brand new particle right where the Higgs was predicted to be. The cautious excitement in that room, you could feel it. They had found a new boson. But was it the Higgs boson? To find out, physicists spent the next year running a kind of rigorous cosmic identity check. They checked its spin. It had to be zero, which is really weird and unique for a fundamental particle. And it was. They checked its charge. It had to be neutral. It was. And crucially, they checked if it interacted more strongly with heavier particles. That's the defining feature of the whole Higgs idea. And it did. One by one, this new particle ticked every single box. So, they found it. The hunt was finally over. But what did this discovery actually mean for us, for our understanding of the universe? I mean, why does this one particle matter so much? Well, the discovery was just profound. First off, it totally validated the Standard Model by confirming its weird and wonderful mechanism for mass. It proved that, yeah, nature really can hide its underlying symmetries from us, and amazingly, it revealed a brand new type of particle, a fundamental scalar particle, one with no built-in spin. That's something we had never, ever seen before. It completed the picture, but it also gave us a powerful new tool to start searching for what might lie beyond it.
But here's a mind-blowing twist for you. While the Higgs field gives mass to fundamental particles like quarks, it is not the source of most of the mass you and I experience every day. Take a proton, right? A building block of every atom in your body. About 99% of its mass comes not from the Higgs, but from the raw energy that binds its quarks together. Think about that. Our substance, our very mass, comes from two completely different cosmic sources.
And as it so often does in science, answering one enormous question just opened the door to an even bigger, more mind-bending one. The precise mass of the Higgs, the very number they worked so hard to measure, pointed to a startling and frankly kind of terrifying possibility about the fate of everything. The data suggests our universe might exist in what's called a metastable state. Okay, think of it like this. It's a ball resting in a small dip on the side of a much deeper valley. It's stable for now, sure, but a tiny quantum fluctuation, maybe billions of years from now, could tip it over the edge. It could cause the entire universe to collapse into a new, more stable reality. The very particle that explains why our universe has substance might also be a clue to its ultimate fragility. What a thought to end on.